morning, friends. As you know, I am in process of the course Aircraft Stability and Control. Today, I am in lecture number 47. This is the tutorial 7, Numerical on Aerodynamic Center and Control Deflection. In today's lecture, we have 3 numericals. In these 3 numericals, we will be trying to find out, with the help of numerical, to find aerodynamic center, determination of Cm0, determination of control deflection, in this lecture, these questions to be answered in this lecture: what is aerodynamic center, what is Cm0, and effect of control on stability. These questions we will be trying to answer in this lecture. Before I start my numerical and its solution, I should start with my Man Ki Baat. And if you see that we have covered aircraft longitudinal static stability. In aircraft longitudinal stability, first we have to understand what is that longitudinal static stability. This is the one model of aircraft. In this model, if I see that aircraft is flying like this ahead, and if there is a gust, we are assuming from the bottom some additional wind has come, and this wind has lifting up like this. So the attitude of the nose will go up. And if this disturbing wind is removed, and if we see that the nose of the aircraft is trying to come to its original position like this, and if AC is behind, this will nose, the moment will be anti-clockwise direction from this side to this side, nose will go down. So we can say that if this type of conditions are there, the aircraft is a longitudinal static stable. Once we talk about longitudinal static stability, in this the contribution of horizontal tail is very important. Most of the wings, their aerodynamic center is ahead of the center of gravity. So if this is the center of gravity and here is the AC, the lift force will act like this, and this will try to make nose up. And just now I told, if the tendency of the aircraft is towards positive nose up or nose going upward, this system is unstable in longitudinal case. So we need something to counter this clockwise moment which is generated by the wing. To do this, we have to fix one horizontal stabilizer, and this horizontal stabilizer are put extreme end of the tail. In this fuselage, at the extreme end, this you can see, at the last we have put, because we want that the distance between aerodynamic center of the horizontal tail and the center of gravity should be maximum. If this distance from center of gravity of the whole aircraft to the aerodynamic center of the horizontal tail is more, the area of horizontal tail we can reduce. So that is the advantage, and so we are placing our horizontal tail at the extreme end. We have seen in our previous classes that the the volume ratio VH. This VH is equal to ST-LT, the area of the tail, the moment arm of the tail, ST-LT, divided by area of the wing and the chord of the wing. So this is called VH, and VH plays very important role for longitudinal static stability. We have also seen the effect of elevator, and we have seen that this elevator makes the aircraft nose up, or the pitching motion. It can make nose up. If I am putting elevator down, a lift will be upward and nose will be down. If I am making elevator up, lift will be downward and this will go up. So if it is in the direct relation with nose up means elevator up, nose down means elevator down. So in this way, this is the elevator, this is the longitudinal stability by the help of the wing and the horizontal tail. But elevators are controlled, and these controls are made to change the attitude of the aircraft, and elevators are used to make pitching up or pitching down. So that is the importance of horizontal tail. So the main function of the horizontal tail is to give Cm alpha negative. That is the objective of the horizontal tail. The effect of the setting angle of wing IW and the effect of the tail setting angle IT is also very important. If we fix the IW and IT in such a way that IW minus IT should be positive. If it is like this, then it will be in trying to stabilize the aircraft. Another important parameter is the downwash. The downwash of the wing plays very important role for stability of the aircraft. So this is for the longitudinal, and in our second module we have seen the lateral and directional static stability. In this we have seen that the effect of location of the wing, if it is the higher winger like this or it is the lower winger as shown here, the higher winger shows a better lateral stability, lower winger shows lesser static stability in lateral. But if you want to make lateral stability with a lower winger, we have to do the dihedral. Dihedral means the wing tip is above than the wing root. So if it is like this, so if this pen, it is showing the dihedral. So if it is wings are like this, means tip is upward, then it is also playing a very important role, and it gives a positive lateral static stability. Same way, the effect of vertical fin is also discussed in our previous classes. So if the wind is coming from this direction, this is called a side slip angle beta, and if this beta is hitting here, a force will be generated in this direction and this will try to move towards the beta. So the positive beta, the nose will go towards the beta and it will neutralize the effect of beta. So it is called a directional stable. However, if you see the lateral stability, so if it is going like this force in this direction will try to make this wing upward. So if you are flying like this, means right wing down. Okay, just you can see here, aircraft is flying like this, and if you are making right wing down like this, then a force, the wind direction will hit here and it will try to reverse back. Same thing, the side slip will be generated, and this side slip will also try to make like this, because this force will give a moment and this moment will try to make again in the same direction. So the effect of the wing, effect of the vertical fin, these are also making laterally and directional stable. Also the wing sweep, it is given here. If you can see here, there is an angle. This angle is the perpendicular to this and this leading edge. There is an angle. This angle is called the gamma, and this gamma or the sweep angle is also very important. As much you give the sweep angle, that much it will be directionally stable. That is why we have seen that modern fighter or bomber aircrafts like B-2 bomber, they don't have the vertical fin. So this, for yawing stability, it is not necessary that we should have the vertical fin. By the help of your sweep, we can alter the yawing stability or directional stability. We can change that thing. Okay, so these things we have already covered. Now we will discuss about the first topic is aerodynamic center. So what is the aerodynamic center? We know that if the flow is coming from here, so the wing will generate some lift, and this lift will be acting in a point. That point is called the center of pressure. However, this center of pressure will vary as per change of angle of attack. But if we select a point where the effect of angle of attack will be neutral, there will not be any effect with respect to that point. That point is called the aerodynamic center. In our first numerical, we are going to solve one numerical. In that numerical, we will see that how this aircraft aerodynamic center is calculated, by the help of which we have already solved during our previous lectures. Okay, so just I am going ahead. So the problem 1 here, it shows that estimate the location of the aircraft aerodynamic center for the A10 given the following values are given. So here S, what is the S here? It is a wing area. S is what? Wing area. In feet we have taken because here all are non-dimensional, so all parameters will be vanishing. And this is the area of horizontal tail. Area of horizontal tail. This H indicate for horizontal tail, and neta H is equal to, this is the ratio of dynamic pressure of tail to the dynamic pressure of wing. Okay, so this is given as a 0.9 because there is a downwash, so this value will not be 1. Here is aspect ratio. Aspect ratio. This aspect ratio is 6.54 of the wing. This aspect ratio of wing. I should write here W. And here aspect ratio of horizontal tail is 3. And d epsilon by d alpha is 0.1. The mean aerodynamic chord C bar is given 8.8 feet, and the location of horizontal tail X, the aerodynamic center of horizontal tail, this is the location of horizontal tail from CG. So if you see here, what is the meaning of this? Okay, so this is the tail, this is the wing. So here is the CG. This is the CG. This is the AC. This is the AC of tail. This is the AC of the wing. This is the LT from here to here. This is the LT. Okay, so this, and you see this d epsilon by d alpha. If it is going like this, there will be a downwash, and this downwash is called the epsilon. There will be an angle. So this, the velocity v here, but if it is reaching here at the tail, this velocity will not be the same. This will be v, and there will be an angle downwash. This is the v prime, and this angle is called epsilon, and it is called the downwash angle. So here the change in downwash angle due to change of angle of attack, and angle of attack is what? Alpha, and this is the alpha. So I have given some picture of this given problem, and now we have to see that how we are able to solve this problem. So in this, neglect any fuselage effect and assume a span efficiency factor of 0.9, means E is given 0.9 for the wing and the tail. To determine the static margin, then Cm alpha and Cl alpha, if XCG is 0.5. So XCG location is given 0.5. Is the aircraft statically stable in pitch or not? So we have to find out that. First we have to find out Cm alpha, then we have to find out Cm Cl, and with respect to the CG, XCG is given 0.5. Okay, so here I can see that I am taking this thing from here to here. This is the 0.5C. Okay, so I think it is in between only, here only. This CG is inside the wing. Okay, so like this. So these problems we have to solve. So first we have to find out the aerodynamic center, the first point. This is the first point, aerodynamic center, XAC of the aircraft. Then we have to find out the static margin, SM. Then dCm by d alpha. Then dCm by dCl. If XCG is 0.5, is the aircraft, and then we have to see that whether the aircraft is statically stable or not. So these are the problem which we have to solve. So the solution of the problem is like this. The equation for aerodynamic center is given by X bar AC. This is the aircraft aerodynamic center is X bar AC of wing fuselage plus CL alpha H divided by CL alpha wing and fuselage. H stands for the horizontal tail and wing fuselage is for the wing. Neta H SH by S X bar ACH 1 minus D epsilon by D alpha divided by 1 plus the same value here. CL alpha H by CL WF. Neta H SH by S 1 minus D epsilon by D alpha. So this is the equation. This is the equation for aircraft aerodynamic center. So if you want to find out aircraft aerodynamic center, that is X bar AC, the X bar indicates that it is a non-dimensional numbers. Okay, so X bar AC. So we have to find out that X bar AC WF plus CL, where CL is capital L means it is a 3D. Okay, here this is the 3D effect. Okay, so this we have to see it is 3D, and here also 3D. But if you see our given conditions, what is, we have to see that. So here given 2D CL alpha is given. Okay, so this we have to see here that 2D CL alpha is given 0.1. Aspect ratio of the wing is 6.54 and E is given 0.9. Okay, so here we have to find the CL alpha of wing fuselage and CL alpha of horizontal tail, and these are the 3D. So we know that from our previous courses, especially from aerodynamics, to find out from 2D aerofoil to 3D wing, the equation for this is CL alpha wing fuselage of 3D is equal to CL alpha of 2D divided by 1 plus 57.3 CL alpha divided by pi E aspect ratio. This 57.3 is to convert degree into radian, to radian to degree. So here it is given CL alpha is equal to 0.11. Okay, here it is 0.11. It is given. So 0.11 divided by 1 plus 57.3, 0.11 divided by pi 3.14. E is given here 0.9 in the problem, and aspect ratio of the wing is given 6.54. So if you do like this, we get CL alpha W is equal to 0.082 per degree. Okay, so same way, if you want to find out 3D CL alpha H is equal to 0.11 divided by 1 plus 57.3, 0.11 divided by 3.15, 0.9, and aspect ratio is here 3. So we will get here 0.0631 per degree. So this is for the tail and this is for the wing. So we got here CL alpha H we got from here, and CL alpha WF we got from here. So this value we have to put here and this value we have to put here. Okay, so we will get this. All the other parameters are given. So I am going for the next slide, and this you can see here that for a subsonic aircraft, such as A10 and neglecting fuselage effect, we know that XACWF is 0.25. The aerodynamic center is at 1 by 4C. So XAC wing fuselage is 0.25, and here it is given that XAC wing fuselage is 0.25, C bar is given 8.8 feet, X bar ACH is equal to what? XACH by C bar. So here XACH is equal to XACH by C bar. XACH is given 26.25 divided by 8.8. So XACH we will get 2.98. So here we are now ready to use this equation which we have given before. So from here we can get the aerodynamic center of the aircraft. Aerodynamic center of aircraft, X bar AC is equal to X bar AC wing fuselage plus CL alpha H divided by CL alpha wing fuselage, neta of horizontal tail, area of the horizontal tail divided by area of the wing, X bar ACH 1 minus D epsilon by D alpha, divided by 1 plus CL alpha H by CL wing fuselage, neta H SH by S 1 minus D epsilon by D alpha. So here you can see neta H is given 0.9, XACH is, we have find out here 2.98. So CL alpha W we have, alpha H we have find out 0.0631, CL alpha wing fuselage, we have find out 0.082. SH is 120 feet square. S is equal to इतने feet square. D epsilon by D alpha is 0.1. Putting this value XACWF wing fuselage is 0.25 plus CL alpha H 0.0631. It is given here. We have just now we have find out this, and wing fuselage is given 0.082 here. Neta H is given 0.9. Area of the horizontal tail is 120 divided by 506. Area of the wing. Then XACH we have find out that XAC by C bar. So X, it is a 2.98 divided by C bar. So 2.98. We have got 1 minus D epsilon by D alpha, 1 minus 0.1. Putting this value, calculating by, we have got the aerodynamic center. We have got here aerodynamic center of aircraft, that is X bar AC. We have got 0.602. This we have got the result. So now you see that the question that we have got from the leading edge of this thing, it is a 0.602, but CG is given 0.5. So we can, from here only, we can find out that the AC is behind the CG. So aircraft will be nose down. Cm alpha will be negative. This is very much clear that aircraft is statically stable. But we will see the further and how we are going to find the other answers. The problem part 1 is completed. Now I will go for the part 2. We know that static margin SM is equal to the difference between XAC minus XCG. This you can see here that if you take the location, the AC is here and XCG is here. So this XAC minus XCG, XAC we have find out the 0.602 minus 0.5, and if it is positive, we got 0.102. It means 10.2%. The static margin is how much? It is a 10.2%. And it is a positive. So if it is a positive, means AC is behind the CG. If it is like this, we can tell that the aircraft is statically stable. Because the static margin is positive, the aircraft is statically stable in pitch. We can also see this because the CG is in front of the aircraft AC. So just now I told you that if you see from here, the AC is 0.602 and CG is 0.5. So the AC is behind the CG. The lift forces, aerodynamic forces will act at the AC, and this will try to make anti-clockwise Cm alpha negative, and this will make the aircraft statically stable. So now to determine the Cm alpha, we will use the equation 1, but first we must determine CL alpha for the aircraft. So we know that CL alpha of the aircraft is equal to CL alpha of the wing fuselage plus CL alpha of the horizontal tail, neta H, SH by S, 1 minus D epsilon by D alpha. Okay, so CL alpha WF, we have find out that it is 0.082. CL alpha H, we have find out 0.0631. Neta is given 0.9. Area of the horizontal tail is 120 divided by 506. Area of the wing 1 minus D epsilon by D alpha. and we got here that CL alpha of the whole aircraft is 0.0941 per degree. So we have found out that the CL alpha of the whole aircraft is 0.0941 per degree. So now Cm alpha is equal to, so we have to find out Cm alpha. So we know that the Cm alpha is equal to minus CL alpha into Sm. And we have found out that this 0.0941 into minus static margin, we have got that 0.102. So if we multiply it, we will get minus 0.0096 per degree. So this we have got the Cm, and it is Cm alpha is negative. So if the Cm is negative, so this we can see from here that this is the AC, your lift force will act, and this is the CG. So this will move the Cm alpha is negative, less than 0, or it is a negative. So in this way, we have find out that Cm alpha is equal to minus 0.0096 per degree, and we know that dCm CL is equal to dCm by dCl, and this is equal to minus Sm. So we have already find out the Sm. So dCm by dCl is equal to minus 0.102. So these things also very important, that dCm by dCl is negative, and if it is negative, the aircraft is statically stable. So I think it is very much clear that the effect of this dCm by dCl we have find out. Now I am going for the next problem, that is determine the aileron and rudder deflection required for an F-15 to maintain a plus 1 degree wing level side slip at 0.9 Mach and 20,000 feet. Determine the value of side force coefficient under these conditions applicable. Derivatives are given below. So here Cy naught is equal to 0. Cy beta, it is a coefficient of force in y direction, and it is mostly applicable to the lateral and directional static stability. Cy beta is equal to minus 0.9056 per radian. Cy delta A is equal to minus 0.0047 per radian, and Cy delta R. So you know that Cy beta means in change dCy by d beta. So the variation of coefficient of side force with respect to the variation of beta is given. Here the dCy by d alpha is given. Variation of Cy when angle of attack is varied, and Cy by delta R is given. This is for the coefficient of the rolling moment, CL, minus 0.0732 by per radian. CL delta alpha is 0.0226 per radian. CL delta R is 0.0029 per radian. If you see about CL naught, this is the yawing moment at 0 angle of attack or at 0 lift. Cn beta is equal to 0.1638. Cn delta alpha is 0.0026 per radian. Cn delta R is equal to minus 0.0712 per radian. These are the given quantity. So we have to determine the aileron and rudder deflection required. Aileron and rudder delta E and delta R to maintain the +1 degree wing level side slip, and speed is given 0.9. So these parameters are given, and we have to find out the rudder deflection and the aileron deflection. So just I will discuss about some man ki baat here. We know that this lift or this rolling moment L is equal to CL Q bar SB, where CL is a rolling moment coefficient, Q is a dynamic pressure, S is the area, and B is a span of the wing. And this CL is equal to summation of the CL naught plus CL beta into beta plus CL delta A into delta A plus CL delta R into delta R. And CL beta here, this CL beta is equal to summation of CL beta of dihedral, CL beta of the wing position, and CL beta of the wing span, and so on. So I am just going to discuss about effect of dihedral and what is the wing position and wing sweep and all. I am trying to discuss its effect first, then I will go for the solution of the problem. We should understand the physics behind all these derivatives of CL beta, CL delta A. So CL beta is dCl by d beta, and this is affecting for whole aircraft, and this is effect of dihedral of the wing. This you can see here, the dihedral of the wing, and wing sweep, then wing position and wing sweep. And just I will I have shown here one aircraft. Here is the dihedral is given gamma here from this axis, from this horizontal plane to this leading edge of this thing is gamma, and this is called the dihedral angle. And if you see that, if you roll this aircraft in this direction, so what will happen? This will generate additional lift in this right wing, and this will try to, and in this side the relative velocity will be less. So this wing will generate the increased lift on the right wing due to gamma here, or because this flow is in this direction, from this direction. So the wing which is facing this beta, this will experience a high gamma or high angle of attack comparing to this wing. So here the lift L1 will be more than L2. So L1 is higher than L2. So this will try to rotate, the left wing will go down and right wing of this aircraft will go up. So this wing geometry and its dihedral effect is shown here. We can see another diagram. Here we have to see the wing position. Here we have the high winger. This is called the high winger. And this is the low winger. So what is happening if the aircraft is high winger, then what will happen for the stability? So this we can see that if the, just I will explain from here, okay, this thing. If aircraft wing is here like this is the wing and it is like this. So if your beta is coming towards the right, so this right wing will experience high relative velocity than this, because it is hitting first here. So flow will go from here like this, and in this side flow will go down because it is upward and it is the downward. So the right wing will experience more velocity, so more lift, and left wing will experience less velocity and less lift, so it will roll like this. So aircraft will generate a negative rolling moment, which is useful for the aircraft lateral stability. The next thing, if you see that the effect of like this wing, which is the lower winger. In lower winger, what will happen if the wind is coming from this side? It will go down and then it will touch here. So in this wing, it will make like this. So it is a positive rolling moment. This is called positive. It means it is further diverged from its given condition. So if the wing is lower winger, it will try to destabilize in lateral direction. So that is the effect of this condition. So now I am going to discuss about the wing sweep, effect of the wing sweep, and effect of the vertical tail moment arm. So first I will discuss about the effect of the wing sweep. So this you can see here. If this is the aircraft, it is moving in this direction, and this is the side slip beta, and here is your sweep, some angle. Sweep is given by this angle. This is the sweep angle. So if you can see that in this wing, the right wing here, it is a right, I am seeing from the top, and this is the left wing. So this right wing will experience more velocity, this vertical velocity. If you see this one and this one, here is very small. So this vertical velocity is only Vn component is high in the right wing. So here it will generate high lift, and here it will generate a low lift. So it will try to rotate in this direction. So it will give, sweep will give, it will give negative rolling moment, or CL beta less than 0. So it is a stable case. So sweep makes the aircraft stable, and it is very useful for the fighter aircrafts or the military aircrafts to reduce the vertical tail, so that the radar cross section is reduced and enemy radars may not be able to capture so easily. Next, I want to discuss about effect of the vertical tail moment arm. This you can see here that in the first case, this is the first diagram, and this is the second diagram. This you can see here that if the aircraft is moving like this, aerodynamic center of the vertical fin is here, and if this will generate a moment, if the beta is from this direction, the force will act in this direction. It is called the negative y direction, and the rolling will be CL beta will be less than 0 or negative. So it is a stable case. So if the aerodynamic center of the vertical fin is above the horizontal plane, this ZV, because this Y into ZV, this will try to rotate this aircraft in this direction. So it will be a stabilizing factor. But the same aircraft, if this theta is increased and this AC has gone down, so what will happen? The force is acting here and it will rotate in opposite direction like this. So CL beta is greater than 0 or positive. So if it is positive, it is an unstable case. So unstable case. So being the same condition, if the angle of attack or the pitching angle is high and AC has gone below the horizontal plane, the same condition, the aircraft may be unstable. But if it is AC of the vertical fin is above the horizontal plane, then it will be stable. So we have to be very careful when designing the aircraft up to what maximum theta or pitch angle your aircraft can sustain for a given condition of vertical fin. So here CL beta of the sweep, CL beta of the fin, these all things we have discussed. Now we have to discuss the solution of the problem, and we know that CL is equal to CL naught plus CL beta into beta plus CL delta A into delta A plus CL delta R into delta R, and we have seen that Cn beta is equal to Cn naught plus Cn beta into beta plus Cn delta alpha into delta alpha plus Cn delta R into delta R, and for the trim condition CL is equal to Cn is equal to 0. So there will be 0 for this trim condition. So these things are given 0. This is also given 0. So CL beta is given 0.0732 1 degree divided by 57.3 in radian plus CL delta alpha is given 0.0226 delta A plus 0.0029 delta R. For Cn, Cn beta is given 0.1638 1 degree by 57.3. This 1 we have in problem, it is given 1 degree side slip angle beta. So 1 degree divided by 57.3, this become radian. So 1 degree divided by 57.3 plus 0.0026 delta A plus minus 0.071 delta R. So we have now two equations with two unknown, and these unknowns are delta alpha here and delta R here and here. So we can very well solve by Cramer's rule or any other rules, and so we have find out that delta A is equal to 0.051 radian, and this radian, if we multiply 0.051 into 57.3, we will get 2.94 degree. This is the angle for elevator deflection. Now how much rudder we have to apply? We got 0.042 radian, that is 2.4. So 0.042 into 57.3. So we will get 2.4 degree. This is the rudder deflection. And it is very much essential to understand what is the effect of this positive. So what is the meaning of positive rudder? Positive means if the right wing is going backward, then it is called the positive. So how it will go backward? It means we should have the force. Okay, so this is the right wing. If the right wing is going backward, it is a positive. So how it will go? So if the force is generated here in this direction, minus direction, it will go like this. So how this force will go in this? So we have to make right side. If your rudder is moving towards the right side, your right wing will go back. So it means you have to deflect your rudder 2.4 degree towards the right. It should be like this. Like this. Initially it is like this, you have to deflect like this. So force will be generated, this wing will go towards the right. Delta A is also positive. So delta A is positive, means right wing going down. Right wing going down is positive. So it means what? Left wing should go down and right wing should go up. So right wing down plus left aileron up should be 2.94 degree. So that much we have to understand, that the right aileron will go down and left aileron will go up in this condition. So we have to understand the physics also. Understanding and the deriving equation is one part, but it is only once or twice you do, it is sufficient. But if you are able to understand the concept of your equations or physics behind the equation, it will be very nice and it will be very useful. The result makes sense from sign standpoint. Left rudder positive is needed to generate a side slip, and opposite aileron positive is needed to offset the rolling moment generated by the aircraft lateral stability. To calculate the side force coefficient, we should use the equation. So understand that the makes sense from a sign standpoint. The left rudder positive is needed to generate the side slip, and opposite aileron positive is needed to offset the rolling. So this, I told that this we have to make down. Okay, and this left rudder we have to make like this. Then only it will be. And that how much force? This is the CY force. So how much CY force is needed? This CY force, how it is generated? Just I will explain a little about this. So if the aircraft is moving like this, the side slip angle beta is here. This side slip angle will hit here. This side slip will generate a force in this direction. This is called the Y. This Y force we have to, this is the CY. So this Y force into multiply Y divided by half rho V square S, you will get the CY. So this CY we have to calculate, and how much? It is a CY naught plus CY beta into beta plus CY delta into delta A plus CY delta R into delta R. So this we have assumed that this is the 0. So minus 0.9056, 1 degree by 57.3. We got this delta A this much and delta R this much. So we got that CY is equal to minus 0.00978. This value we have got. The result makes sense from a direction standpoint. The negative sign indicates a side force in the negative Y direction. Oh, just I told you. If beta is positive, the Y is acting in opposite direction, and it is a positive direction, and this is the negative. So this Y is negative. So the force is acting in this direction, as I told earlier. So the negative sign indicates a side force in the negative Y direction, which is that result from a positive side slip angle. So now determine the crosswind limit of the T-37 assuming a final approach equivalent airspeed of 100 knots and the following characteristics. Okay, so this I will discuss in my next class. Hope you have understood very well, and thank you very much for joining the class. And these are my references: Robert C. Nelson, Aircraft Stability and Automatic Control, NPTEL lectures of Aircraft Stability and Control by Professor A.K. Ghosh, IIT Kanpur. Thank you very much for joining this class. My contact email is ydwidwei@gmail.com. This is my email. You are always welcome to ask any queries related to this topic. Hope this will be useful. Please be tuned. In next class, I am going to discuss further the numericals about the different topics. Okay, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.